Hello, this is Concrete Path. Today's lecture is about the shear stresses in composite beams. Shear stresses in composite beams. So we already have solved a few problems on composite beams, but in the chapter of bending stresses. So let's say that we have the same kind of section, section, that's steel, timber, and steel, and we say that we also call this as a fletcher beam. So we say to get the shear stress at any location I, for that you have this procedure that convert it into or transform it. You use the method of transformation of that section, transformed section. You got the transformed section. Let's convert that timber goes to steel, so we can get the section somewhat in this fashion. So the second one is that after that, get the location of neutral axis. And third is that calculation of that second moment of area about the neutral axis. This is for the transformed section. After that, you want to say what is the shear flow at any location of I, that equals to VA y bar by I neutral axis. Then after that you can get, if you want shear stress at that location I, you would say VA y bar by I, but you can have that, you can directly say what the shear stress at that location would be. You multiply the actual width, you divide the actual width here. If you divide the actual width here, you can get the actual shear stresses here. And if you want to say what is the shear force at that particular location, shear force, that we know that the shear force was equals to F shear was equals to tau T dx or tau B dx. So your shear flow is the shear force per unit length. So if you multiply the length, you can get the shear force Q by some dx. We can say some length of longitudinal length, some length. So we can get also the shear force. So in this one, we say that we install that we drive that bolts. We drive those bolts to make the connection stable. We install that, we drive those bolts in between those members. So let's say this is some bolt, or we can all call it as bolt, we can call it as a nail, we can call it as a rivet. So some sort of connection is driven in between those sections, and we want to say what is the shear force in the bolt, what is the shear stress or shear force in the bolt. We can also calculate that at that particular junction where the two members are connected because of that bolt. We would say what is the shear flow here, shears, we can get the shear stresses and shear force here. So let's take that first problem. Let's take the first problem of that kind. So we have the section of rectangular section. We have the top of steel and bottom of steel, thickness of 12 mm, and this is your timber of 250. Timber is 250. So this is timber. And you are applying on this section, there is some shear force of, let's say the shear force V equals to 4 kilonewton on this section. So a vertical shear force of 4 kilonewton on this section. And if you have this in the longitudinal direction also, this section, I would say there is some continuity also. And I would say there is one concept, that is, we say that spacing of those bolts or nails. Let's talk about bolts. So you drive a bolt here. So this is some bolt you drew. There is some bolt, and similarly from the bottom there is some bolt. So you drive the bolts here. And our problem is that you need to get the shear stress, average shear stress in bolt. because of that vertical shear force of 4 kilonewton. So I would say tau average means because your bolt is from the top to some depth inside the timber. So we say that we take the value just at the junction because your problem gets easier. If you take at the junction, we can say that's your tau average. If you calculate the shear stress at the junction, we can say that's your tau average. So if we talk about the section, we have the width also. We have this width of the section is 150 mm, and diameter of the bolt equals to 12 mm, and you want to say what is the shear stress in the bolt. Now the first step is that if you convert it into one of the into one of those members, let's say if you convert that timber into steel, that means that the thickness of that timber would be equals to that timber. Initially the length width was 150 and you have to multiply the modification factor. That means you are converting from timber to you are converting into steel. So you say what's the value of ET and ES. So value of ET and ES is such that this value would be equals to 1 by 20. We have that this is your 10 to the power 4 megapascal divided by 2 into 10 to the power 5 megapascal. So that's your 1 by 20. So you divide that, so you got a value of 7.5 mm. So that means that equivalent width of the section, if you replace the timber by steel, you have to just use 7.5 mm of steel in place of that 150 mm. So if you take that section now, so this was your thickness of 12. This was your 12 thickness. Similarly, this is your 12 thickness. After that, you have this some thickness of 7.5 for a length of 250, for the depth of 250. Then after that you have that same material. So this is 12. This is the thickness here is 7.5 mm, and the top is equals to 150 mm. And now I would say because the section is symmetric, I can calculate that I would say directly that the neutral axis at the midspan is at the midsection. So the neutral axis, so the top, from the top we would say neutral axis is at a distance of 250 plus 12, 125 plus 12, 125 plus 12. That's 125 plus 12. That is 137. 137. Now the thing is that next step is that calculation of moment of inertia about the neutral axis. I would say that assuming that it is all entire rectangle, of dimensions b and d cube bd cube by 12 minus, you have to subtract the two values. You have to subtract the two values of that 2 times, or we can say directly the total is 150, total width is 150, and you have to subtract the thickness of that web 7.5, and you are left with that width. B at D is equals to 250 cube by 12, and you can get the value of that neutral that second moment of area, that is equals to 71.589 10 to the power 6 millimeter power 4. So you got this value of I neutral axis. Now your problem is that get the value of shear stress at that junction. So for that, if you get the shear flow at that junction, let's calculate the shear flow at that junction. So your junction is this one. So if I write that shear flow at the junction, that would be equals to V A y bar by I neutral axis. So we had that shear force of 4 kilonewton, shear force of 4 kilonewton. And if you need to calculate that AY bar from the neutral axis, well, let's have that value of AY bar from the neutral axis. This is that AY bar of area equals to 100 into 12, and the centroid is here at a distance of y bar. So your y bar equals to this one is your 125, and this one is your 6. 125 plus 6, 131, 131, 131, 131. Yeah. So let's write that also. So I would say into that area of 100 into 12 and acting at y bar, that is 131 mm power 3. Similarly, divide by that INA, the value of INA we got 71.589 10 to the power 6. 71.589 10 to the power 6 millimeter power 4. And you can get the value of shear flow at that junction. Shear flow equals to 13.175 kilonewton Newton per millimeter. This is your Q at the junction. So if you want that shear force at that junction, I would say what is the total length between those? What is the total length between those two bolts that we call as spacing of bolts? So it's saying that after a spacing of 200 mm, there is one more bolt. There is one more bolt in the same fashion. Similarly, after that, one more 200 millimeter, there is one more bolt. Similarly, it goes on and on. Similarly, from the bottom side also. Similarly, in this way. So we say that the spacing between those two bolts, that's 200 mm. That we call as pitch. We call it as a pitch of the bolt. Pitch of bolts. Pitch of bolts. That's 200 mm. I would say that contributing length or contributory area would be equals to 200. If you take for the, let's say if you take for the mid bolt, I would say from this side 200 by 2 and from the other side 200 by 2. So this area would be contributed by this. So I would say 200 in a length of 200 would be contributed by one bolt, 200. But the end ones will contribute only 100 or 100th, that only 100 of that length at the ends. But if you talk about the mid values, mid sections, I would say the pitch would be equals to 200, and it will contribute also 200. The length of 200 will be contribute 100 from one side and 100 from other side. So a pitch of 200, if you multiply that, so I would say Q J into pitch, or we can say spacing of the bolts. That's 13.175 Newton per millimeter into 200 millimeter. So you got the shear force at that junction. That's equals to 2635 Newton. And now the question was that get the value of shear stresses in the bolt. Average shear stress in the bolt, and the diameter is 12 mm diameter of the bolt. Now if you take that shear stress in the bolt, let's say that is average shear stress at the junction, that equals to shear force divided by that area. So we got that shear stress of 23.31 megapascal. Let's take one more problem. We have that section of, we have this section. Let's have this section. Let's have that section. Let's have that section. So we have this section. Now the dimensions are that you have the dimensions that the thickness of those, let's say this is 18 millimeter, this is 18, and similarly this one is also 18, and this one is also 18, and the spacing between that, the length of this part is your that's 76 millimeter. And similarly from the top also we have these same values, 18, 18, 18. So the total depth is 112. Total depth of 112 millimeter. So the thing is that you have this, you have driven the bolts, you have driven 4 bolts. Let's say if this is 18, the diameter of bolt is some sort of, let's say 12, 16. So the diameter of the bolt is somewhat in this fashion. Let's say this is the bolt. Let's say this is the bolt. This is the bolt, and next one from this other side, we have same sort of bolt. So this is the bolt, and from the other side also, so this is some bolt. From this side also, we call this as head of the bolt, and this is your shank part of the bolt. So there we have 4 bolts driven in that section, and the section is subjected to a shear force of 2.5 kilonewton. This is some section, and we have applied a shear force of 2.5 kilonewton. And the spacing, we have the spacing between those bolts in the longitudinal direction. Let's say this is section. We have bolts, and the spacing between those bolts is that we have the spacing of 44 millimeter. That means after every 44 millimeter of the longitudinal span, I would drive those bolts. 44. Now the thing is that you need to get the shear force in the nail. You need to get the shear force in one nail. How much shear force is in one nail? If you see that by the symmetry, if you can solve either one of those, if you take any one of those bolts, you can get the shear force. You can get the same value of shear force in each of those bolts. You can get each shear force in each of the bolts equal. So that's why it's saying that get the shear force in the nail. That means you can take any one because of the symmetry. If you see that this is 76 plus 18, that is also equals to 112 millimeter. Now, if you take that because during the derivation we take the area above that neutral axis. If you take that, if you see from the neutral axis, we have 2 bolts on the same level. So I would take any particular. Let's take that area above, and that also at the junction. If you analyze this area where the 2 members are connected by a bolt, similarly we have 2 bolts for this particular area. If I get the value of shear stresses here or shear flow here, then I can say what is the shear stress, what is the shear force in the bolt. If I get the shear stress at the junction, so if I take this area and I calculate the shear flow for this area, then I can get what is the shear force or shear stress in the bolt. Let's have that. This is neutral axis, and from that the centroid is here. Area of that section is equals to 76 into 18. This is your section of 76 into 18. So the centroid is at a distance of, see, the total depth is 112. That means this part equals to 56, and we have this thickness of 18. That means 56 minus 9, that's 45. So the centroid is at 45. So this is 56, and this is 18. So the centroid is at 45. 56 minus 9, 47. 56 minus 9, 56. 56 minus 9, 47. 47 millimeter. So 47 millimeter you need. So if I calculate the shear flow at that junction, that would be equals to a shear force of V. A shear force of V equals to 2.5 kilonewton. Shear force of 2.5 kilonewton. 2.5 kilonewton, and area into y bar, the area was equals to 76 into 18, 76 into 18. This is area of, and the centroid is at 47 millimeter from the neutral axis, divided by value of I, the value of I about the neutral axis. Can you calculate the value of that I about the neutral axis by the symmetry? By the symmetry, can you say we have two? We can assume that this is some bigger rectangle, and you subtract the smaller rectangle. I would say bigger rectangle of 112. We have width equals to depth 112. BD cube by 12. Then I can write a to the power 4 by 12 because it is a square, and then you have to subtract the smaller circle you have. That is a dimension of 76 from both the sides, 76. So I can write 76 power 4 by 12. So I can get the value of INA equals to 10332 10 to the power 3 millimeter power 4. So I got these values. Let's take this value and use that on the top. So we got the value of shear flow. That comes equals to shear flow equals to 15.6 Newton per millimeter. And the question was that, question says that get the shear force in the nail. If you want to get the shear force in one nail, but the thing is that you got shear flow, but at the junction, where we have at the same level we have two bolts, bolt 1 and bolt 2, So if you get the shear force for this length, if you get the shear force for the pitch of that 44, total 44, that is resisted by 2 bolts, I would say. That is resisted by 2 bolts. I would say total shear force, F shear, that's resisted by 2 bolts. I would say resisted by 2 bolts. 2 bolts would be equals to, or not resistor, I would say that shear force developed here would be that the bolts would be subjected to that shear force of that Qj into 44. Qj into spacing or pitch. Qj is your 15.6 Newton per millimeter into your pitch of 44 millimeter. So you can have that value of shear force equals to 684.5 Newton. But the thing is that it's we can write 2 nails at the same level, or at the same junction. So you can say shear force per unit per nail or per unit nail, that would be equals to 1 by second of that shear. That would be 342.25 Newton. 342.25 Newton. So in the concept of that, we had already talked about the shear center. For the concept of shear center, we say that the shear center, if you have two symmetrical axes, we say that at the intersection of those we have shear center. If the members have one if the members have one symmetrical axis, then the shear center would be along the principal axis, somewhere. Similarly, if there were two narrow intersecting sections, I said that the shear center would be at the intersection of those two lines along the center. So this was shear center. There was one thing that I forgot at that time. So that is this Z section. Let's say this is symmetrical Z section. We say that because there is no symmetry, it lacks the symmetry. I would say the intersection of those two narrow sections. But here we have 3 narrow sections. Then if I take that intersection of this one, then intersection of this one, and intersection of this one, then the shear center follows some point is developed there. We say that this is the shear center for this case. This is some, I would say this is some exception from the other examples. So this is some different case of that shear center. Now one more, that for the vertical loading, we say if you have the, let's say you have this channel section and you are applying a vertical transverse shear force, vertical, and for that we say the shear flow variation for the in the horizontal or in the flange, that would be some sort of linear variation, in this way, or you can say in this way, a value of Q naught here, Q naught. And similarly for those sections in the vertical, I'd said there would be some shear force here, then it goes by some parabolic nature, so there is some shear flow. But if the loading is not in the same way, let's say you have the same section, let's take the section as the same. Now you are applying load in this direction. Or you can say you have this section in this way. If load is applied in the horizontal direction, F in the horizontal is a shear force, but it is in the horizontal direction, then the shear flow would be in this way, that it's your horizontal. I would say this is your horizontal now. Now the shear flow would be for the actual horizontal, it would be in the form of parabolic. So there is some Q naught. Similarly from the bottom, there is some Q naught. If you similarly take that I section, now the load is not in the vertical. Load is in the horizontal. A shear force of V. We say that the shear flow in the flange would be, that would not be a triangle. That would not be a linear variation. That would be a parabolic variation that we have already checked. That's a parabolic variation. So this is some different aspect of that shear flow. So this is the end of that concepts and the end of that chapter, shear stresses, shear flow, and shear center. Thank you for watching this series.